this video, I'm going to briefly explain the rotational inertia around the center of a hollow disc, like a ring, and then one of a solid disc. So we're going to start with our hollow one. And basically, this is going to be our ring, and this is going to be our R. So we're going to start by writing the equation of inertia. So we know that inertia is equal to mr squared. Well, we want to think about this. So because this is a ring, all the mass is going to be uniformly distributed around like the outside of this. So all the mass is over here. There's nothing inside because it's hollow. So what we can do is we can break all these masses into really, really small pieces, which will all have a really, really tiny mass. And they're all going to be a radius from the center, distance r from the center, which is a radius, but in our thing it's r. So how we're gonna add this in our equation is that we're gonna say di, which basically is saying a really small piece of inertia, a really small amount of inertia, is gonna equal a really small amount of mass, and then r squared. I lied. It's going to be capital R squared. So now we're going to be playing variable versus constant. So the R squared is a constant, and we're differentiating with respect to m. So we're good. So we're going to take the integral of both sides. The integral of di is just going to be I. This is a constant, so we're going to bring it out. It's going to stay the same. And the integral of dm is just going to be m. So that's how we get I equals r squared m for a hollow disc, or like a ring. So now we're going to go to something a little bit more complicated. So what if this wasn't hollow and it was actually solid all the way through? So like a coin or something. Oh no, that's okay. So I'm going to draw the picture again. So this is going to be our solid disc, and this is going to be our capital R. But now what we want to think about is this entire thing is shaded. So we can't, if we break these into small pieces of masses and do the mass inertia and stuff, the outside will be a distance of r, but there's also a bunch of masses over here. There's a bunch of rings. So what we want to think about is dividing this into many, many, many rings. So let's make that's a really bad circle, but pretend that's good. We're gonna break it into really, really tiny width rings, and they're all gonna be an r distance, like a small r, and that's gonna be changing depending on which ring we're actually calculating for. And then what we're gonna do is we're gonna break these individual point masses into small dm's, and we're going to calculate it like that. So let's see what we get in our equation. So again, we start with I equals mr squared. Well, these all will still have a small inertia value. M is still going to be a small mass, and R, well, it's going to be lowercase r. So now if we play variable versus constant, we see that this r is also a variable, and we're integrating with respect to m if we do take the integral of this. So that's an issue because we have two variables and only one equation. So what we want to do is we want to think about how we can replace dm with something that has dr in it. So we only have, so we're integrating with respect to the variable that is the unknown. So how we want to think about this is we're going to make another equation. We're going to make a new variable. So suppose we write sigma. So this is going to be our density. It's going to be mass over our area. So if you think about this, the mass is just uniformly distributed throughout this entire object. So the density of this ring versus the density of this outer ring versus the density of this entire disk, it's all going to be the same. So what we want to do is we want to find the density of this entire disk, and then we're going to make that equal to the density of our small ring, and we're going to see if that helps. So the density of our, let's do our disk first, our entire disk. That's going to be equal to the mass, which I should have written before, but capital M is the mass of the entire disk. So that's going to be our capital M over our area. Well, that's just pi r squared. It's going to be capital R because this is big R. Our density for our rings is going to equal something a little different. So our masses will be dm, but our area is a little different. So we're not actually solving for the area of this entire circle. We're only solving for the area of the actual ring itself. So what we're going to think about is if we cut this ring like right there and we like lay it flat. So if we lay this ring flat, we'll get something like this with a really, really, really small thickness. That thickness is what our R is kind of representing. That's going to be dr. And what's going to be the length of this? Well, it comes from a circle, so we're going to think about the circumference of the circle. So we're going to think about like, it's almost if you like took a piece of paper and then you like made it into a circle. The circumference is going to be the length of that piece of paper, basically. So we know that the circumference is going to be 2 pi in lowercase r, which is that r. So now what we can do is we're just going to multiply these two together to find our area. So it's going to be 2 pi r d r. Now what we can do is we know that the density of these two are the same. So we're going to equal both of these together and see if we can find an equation for dm. So we're going to have capital M over pi capital R squared. You want to make sure like capital R is different from lowercase r. And then you're going to equal that to dm over 2 pi r dr. So I'm going to go ahead, I'm going to do this in a different color. First, I'm going to go ahead and cancel the pi's. So what I'm going to get left, and then I'm going to multiply this entire thing with this side. So I'm going to get dm equals m, and then we're going to multiply this entire thing. So 2r over capital R squared, and then dr. So now that we have this thing, we can plug dm into this dm. So what I'm going to do is I'm going to write m 2r over r squared. I'm going to leave a little bit of space, dr, and then we're going to write everything else. So r squared, and this equals di. So everything in blue is just coming from the top equation, and then everything in green we're just plugging in for dm. So before I integrate, I'm just gonna like clean this up. So di equals, I'm gonna bring the 2 out. So 2m r to the third over capital R squared dr. So now we're gonna play variable versus constant again. So we have a capital R squared. So capital R is a constant. So that's going to stay the same. It's like a known, basically. Lowercase r, well, that's a variable. So that one's a variable. And then capital M, that's also a constant. And then obviously 2 is a constant. And we're differentiating with respect to lowercase r. So we only have one variable in this equation, which is what we want. Then we're going to take the integral of both sides. I'm going to leave this 2 out because it's a constant. You're going to get I equals, so the 2 stays out, m is a constant, capital R squared is also a constant, so I'm going to keep all this out. So we only really are integrating r cubed. And how we do this is we add on to the exponent, and then we're going to divide by that number. So 3 plus 1 is 4. You're going to divide by that number, so you get 1 over 4, and then r to the 4th. So that's going to be our entire sort of equation. But these integrals are going to have bounds. So these bounds are going to go from 0 to capital R. So what this is basically saying is that each ring, our starting ring is going to have a zero like value R value. It's going to be like that one. Then as we go outside from that like origin, our R is going to keep on increasing until it hits this outer one, which is a capital R. And we're going to stop there, and we're going to add all the inertias we find together at that point. So we're going to have from 0, which is going to be our smallest ring, like radius, to capital R, which is our biggest ring radius. So basically going to evaluate this from 0 to capital R. And I'm sure you know how to do this, but we're going to plug in the capital R first, and we're going to subtract it by what we get when we plug in our 0. So 0 times 0, blah, 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 that's 0. So I'm not even going to bother doing that. I'm just going to plug this capital R into this equation. So we get I equals 2 m over, my bad, that's supposed to be a capital M, over capital R squared times 1/4, and then we're going to bring that capital R in for this lowercase r, and to the 4th. So now if we simplified this, the 2 over 4, that becomes 1 over 2. The m stays constant, and then there's 2 r's on the bottom, there's 4 r's on the top, so that becomes r squared. And that's how we get the inertia for a solid disk is 1/2 m capital R squared.